The reactor used in this experiment is a continuous stir tank reactor, which operated in steady state. This CSTR consists of a tank which operates at constant volume. Additionally, in CSTR, the reactants and products flow in and out continuously. Furthermore, prior to the CSTR designs, it consists of a feed and exit stream to introduce and remove the products. Since it is well mixed, the contents will have constant properties throughout the process. The conditions in reactor exit streams are the same as the one inside the streams. The stirring blades, called the agitators, are used to mix the reactant, and it is responsible to ensure a well mixing in order to produce a uniform concentration throughout the process. The distribution of residence time is represented by an exit age distribution, ET. In order to calculate the residence time, the volume of the tank by the average volumetric flow rate. These are the basic concepts of the CSTR. The first objective is to study the effect of step change input on the steady state of the system. The second objective is to study the effect of pulse input on the steady state of the system. And last but not least is to investigate on dead time coil on the steady state of the system. The general mole balance equation is given as in minus out plus generation equals to accumulation. The formula is denoted as FA0 minus FA plus the integration of RA dV equals to dNA dt. On the other hand, in terms of conversion, the volume is equal to FA0 minus FA over negative RA, and in terms of derivation is we get FA0 X divided by negative RA at the exit. For step change input, the cumulative distribution denoted by F as a function of T is simply as C as a function of T divided by C0, while for step and pulse responses of a reactor are related by the following. F as a function of T is equivalent to the integration of E as a function of T dt, and E as a function of T is equivalent to the derivation of Ft divided by dt. Well, for pulse input, this method required the introduction of a small volume of concentrated tracer at the inlet of the reactor for 2 minutes only. The resident time distribution curve can be obtained by computing the individual exit age distribution using the following formula. E as a function of T is equivalent to C as a function of T divided by the integration of limit from 0 to infinity, C as a function of T dt. Last but not least is the resident time distribution. The distribution of resident time is represented by an exit age distribution denoted by E as a function of T. The function E as a function of T has the units of per time and is defined such that the integration of 0 to the infinity, E as a function of T dt equivalent to 1. On the other hand, the average resident time is given by the first moment of the age distribution. T denoted as T bar equals to the integration of 0 to infinity T E as a function of T dt. Continuous stir tank reactor has its own advantages and disadvantages. Firstly, in the advantages, it is a continuous operation, it has a good temperature control, it can easily adapt to two-phase run, and last but not least, it has a simplicity of construction. While on the other hand, the disadvantages can be seen as it has a lowest conversion per unit volume, and pipe passing and channeling is possible with poor agitation.
In this CSTR, we have 3 reactors: Reactor 1, Reactor 2, and Reactor 3. These 3 reactors are made up of borosilicate glass with 2 liters capacity each. It has speed stirrer, temperature and conductivity sensor in each reactor. Overflow tubes are also provided in the second and the third reactor. For the stirrer system, it consists of a variable speed stirrer system with digital display consisting of a motor and a shaft with impellers made of stainless steel. The feed tanks consist of feed tank 1 and feed tank 2 with a capacity of 15 liters each. Feed tank 1 is filled with deionized water from the water deionizer, whereas feed tank 2 is filled with sodium chloride solution, which is prepared beforehand. Each tank has a feed pump to transfer the liquid from the feed tank to the reactor. Also, there is lever switch fitted in each tank to protect the pumps from dry run. The waste tank is a rectangular tank with 50 liters of capacity made up of stainless steel. It is placed at the bottom of the equipment. The date time coil is made up of stainless steel tubing. It can hold up to approximately 200 ml of the solution. The flow meter has a LCD display. It is ranged from 0 to 500 ml per minute, and the output is ranged from 0 to 5 VDC. The data acquisition system consists of a personal computer, ADC modules, and instrumentations for measuring the process parameters. All analog signals from the sensors will be converted by the ADC modules into digital signals before being sent to the personal computer for display and manipulation.
Ten liter of 0.025 molarity of sodium chloride solution is prepared before starting the experiment. The apparatus is shown as on the screen. Feed tank T1 will be filled with the ionized water, while T2 filled with sodium chloride that we have prepared earlier. Ensure that valve V6 is closed. The main switch is switched on. The position of valve V3 is set towards pump P1. Valve V5 is open. Pump P1 will be switched on to fill up the 3 reactors with the ionized water, and valve V4 is adjusted to obtain a flow rate of 150 ml per minute. Stir rod 1, 2, 3 from respective reactors is switched on and are set to approximately 200 rotations per minute. Pump P1 is switched off and valve V3 is quickly set towards pump P2. Pump P2 is switched on and start the timer simultaneously. We then open the data acquisition system. The cursor is directed towards data logging and experiment A is clicked. Conductivity values of CT1, CT2 and CT3 is recorded at suitable interval. Continue recording all the conductivity values until all readings are almost constant. Lastly, we switch off pump P2 and close valve V4. In order to drain all the liquids in each reactor, valve 11, valve 12 and valve 13 are closed. Pump P2 is operated for 2 minutes and then we switch off pump P2. The 3-way valve is set towards pump P1. Then pump P1 is switched on and let it run until the end of the experiment. Valve V3 is set towards position pump P1. Ensure that valve V5 is closed. Then, we open valve V6, followed by valve V10. Pump P1 is switched on. Valve V4 is adjusted to obtain a flow rate of 150 ml per minute. Stirrer at reactor 3 is switched on and the speed is set up to approximately 200 rpm. Pump P1 is switched off and valve V3 is quickly set towards pump P2. Next, we switch on the pump P2 and start the timer simultaneously. We open the valve V10 and partially open valve V15 to get the right flow. Lastly, we switch off pump P2 and close valve V4. In order to drain all the liquids in each reactor, valve 11, valve 12 and valve 13 are closed.
Sodium hydroxide, which is a tracer, is injected to determine the transient behavior of CSTR in series. The tracer can be injected by two ways. First, step change input, and second, pulse input. Since the value obtained are in terms of conductivity, this graph, conductivity versus concentration graph, enables us to convert any conductivity of NaCl to the exact concentration. For the first part of the experiment, we are going to determine the effect of step change input. This is the graph of concentration versus time. Since this is a step change input, there are two steady state values, which are the initial and final steady state value. The system is initially at rest before the concentration is introduced, which causes the change in equilibrium. Over a period of time, the system will approach a new steady state value and being at rest again. This graph shows the relationship of residence time distribution over time. The area under the curve represents the amount of tracer resides in each reactor. In the second part of experiment, we are going to investigate the effect of pulse input. From the graph, reactor 1 shows the highest increase of concentration during a short period of time, as the pulse is directly channeled to it before the value drops significantly until it reaches a steady state. The concentration will start to decrease as it is going into reactor 2. Eventually, the final concentration in reactor 3 is higher compared to reactor 1 and 2 as the concentration stays longer due to better distribution of concentration in the last reactor before it is being discharged. In the first reactor, the residence time distribution suddenly dropped to a minimum value when the pulse of tracer is injected suddenly for 2 minutes. This suggests that the sudden increase in concentration results in lower time span of the tracer in the reactor. After around 10 minutes, the RTD in reactor 2 will start to decrease but at a slower rate compared to reactor 1 because the tracer passed through reactor 1 before going into reactor 2. In the last part of the experiment, we are going to investigate the effect of the dead time coil. In this experiment, we are only using reactor 3 as it is connected to the dead time coil in parallel. For the purpose of this experiment, we are going to use two pulse input. The first pulse is injected at time equal to 0 and then we waited for it to reach a steady state. A second pulse input is injected, but this time around we are allowing the tracer to flow through the dead time coil to create a stagnation zone that exists in the real reactor. The residence time distribution suddenly dropped to a minimum value when the pulse of tracer is injected suddenly for 2 minutes. The sudden increase in concentration results in lower time span of the tracer in reactor 3 for both pulse input. The stagnation zone reduces the effective volume of the reactor, leads to the decrease in RTD. The RTD will then increase over time until it reaches a steady state value.